Hello, my name is Chuck Hayes. I'm from Swagelok Company, and today we're going to be discussing fluid system components for H2 applications. Just quick introduction for myself. I've been a veteran at Swagelok for about 31 years, and we are a world leader in the development of fluid system components, assemblies, and services. I've spent about 25 years in new product development, and we're going to talk about that a little bit, and as I explain some of the elements of creating products that are able to seal well within the hydrogen environment. You can read some of the other goodies up there, but one of the important parts is I do work as an active member for Canadian Standards Association, where I sit as the vice chair for hydrogen standards in North America. I'm also a part of the ISO TC 197 committees, technical committees for international standards. But with that, let's just get moving right into the important stuff. So, why is it that fluid components matter when we're talking about hydrogen and hydrogen fuel systems? Well, a couple of basics when we talk about hydrogen fuel systems. When we deal with on vehicles, we're storing hydrogen at pressures that are pretty significant, between 250 and 900 bar. So 900 bar is, close to 14,000 psi. It's a lot of pressure to be storing under. So we're dealing with a lot of pressure of a small molecule gas. And when we're dealing with vehicles, we're primarily dealing with things that have to withstand fast speeds, bumpy roads, inclement weather conditions, salt on the roads, corrosion, lots of different elements that come in from being out in the environment, as well as all of the different things that make that come in from the road itself. Safety is very important. Refueling stations have to be safe for the average consumer. Usually, when we talk about dealing with high pressure industrial gases, those are being done by professionals behind a wall at a refinery or at a chemical plant. And those people are highly trained, wearing yellow vests and know what they're doing. But think about it. You can end up having someday a hydrogen vehicle that your grandmother can go up and pick up a nozzle and plug in and fill a high pressure tank with and be standing there between a dispenser and a vehicle. It's a little bit different world that we're playing in than when we're usually playing in with high pressure gases. Usually, high pressure gases, the highest pressure we ever get is your propane tank on your gas grill in your backyard, and this is much different. So, of course, maintenance is really important when you're dealing with systems like this, and you've got to be able to have leak-free joints whenever you're servicing. So, quality is critical in tube fittings to deliver leak-free performance. We're primarily going to be talking about fittings today and fitting technology. So what's unique about hydrogen? Well, hydrogen is one of the smallest molecules in nature. Hydrogen comes when we see it. In most cases, it'll be H2. There'll be two hydrogens together. There is actually one molecule smaller, which is helium, because helium comes as a single atom, and it is slightly smaller. But they're very small to start with. And we'll talk about small molecule gas a lot in this presentation because it is the critical item that makes designing for hydrogen important. Now, what's important when you're dealing with tube fittings and leak connections and connections that don't leak for hydrogen? Well, safety. Of course, escaping gases can cause certain safety risks. And again, I mentioned before about the end users interacting with dispensers during your refueling. But of course, there's efficiency as well. So you want to be able to efficiently be able to move your hydrogen around without losing lots of pressure, with tons of pressure drops, with tons of other issues there. And then, of course, you don't want the waste. So losing hydrogen to the atmosphere under pressure or not pressure means you're wasting a valuable product that you've created, as well as, well, wouldn't it be awful if you had leaks in your system if you had a car or an 18-wheel truck and you went and slept for the evening, came back out in the morning, and all the gas has escaped, and now you can't go anywhere because you have no gas in your tank. So efficiency and no waste are really important. Finally, there is an issue about hydrogen embrittlement. Hydrogen embrittlement, in the simplest terms, means that hydrogen can affect certain metals. It does affect polymers and plastics as well. But what it can do is degrade those materials so they would fail earlier. Lots of different ways to do it. This is in the metallurgy class today. I just want to make you aware that hydrogen affects materials. And there's ways to be able to protect it. One of the common and the traditional way, back in the 1800s when they had coined the phrase hydrogen embrittlement, it was thought that hydrogen caused cracks. Cracks in pipes would cause them to fail, and therefore hydrogen caused failures. It's not quite true today. We understand a lot more about it, but hydrogen can help cracks propagate faster. My little graphic on the side kind of gives you an idea of the size relationships between hydrogen. So hydrogen is kind of is in a relationship to a golf ball, is equivalent to the golf ball in the relationship to the planet Earth. So if you think about those relationships in three dimensions, that hydrogen molecule is very, very small. So how many golf balls would go on the planet Earth is kind of equivalent to how many hydrogen molecules could fit in a golf ball. Um, we mentioned safety a couple of times, and that's about all we're going to talk about in safety. If you want to learn more about safety, I really recommend that you go out to the Center for Hydrogen Safety. It's a US-based consortium with tons and tons and tons of great information. Their website is h2tools.org, and you can peruse tons of information dealing with how to safely handle hydrogen, how to transfer it inside stations, what offset rules are, and lots of other issues there. Doesn't really get into design as much as the other requirements, but it's a great place to go learn about hydrogen safety in industry and in consumer. So let's go back and talk about leaks again. So leak integrity and quality. So think about this. Hydrogen fluid systems can leak for a variety of reasons. You can get leaks in sealing areas. You can get leaks in something called permeation. But good designs can really help mitigate this risk. And but unfortunately, not all solutions are created equal. And we're going to go through a bunch of different designs to give you some basics so you understand where to make the most appropriate choices for uses within your hydrogen systems. So let's start at the very basics. Okay, we're going to start talking about leaks and leak conditions and how to describe them. So the first one we're going to talk about is continuous pore structures between mating surfaces. So if I take two machine surfaces and push them together, what you'll notice is that there's always hills and valleys within them. If you were to think about taking, two pieces of concrete together and pushing them together, what you'll see is the surface of concrete, if you look at it, is very rough, and there's hills and valleys and pits and voids and things like that. And if you try to push two of them together, that you're not going to get those two to seal together. A little bit difference is if you put two pieces of glass together, they get very, very close in structure between them, and you can actually wring them to the point that they will stick together because they're very, very smooth. Well, when we machine parts out of steels, unless lots and lots of work is done to make them super smooth afterwards, there's a surface finish that takes place. And what you see is that in order to get a good seal, that material, those hills and valleys need to be knocked down as much as possible. Because when you have two hills hitting each other, you have valleys that now cause pores or porous structure. And what can happen if there's enough of those is that you create a continuous pore structure where gas can go ahead and flow between all these little voids at your sealing area and cause leaks. The size of that leak can be determined by measuring how much gas can pass through there. So how do you deal with this when you're trying to make something like an all metal fitting? Is that you go ahead and you deploy plastic deformation. So you move the materials in such a way that they will create a seal on those surfaces. And the Swagelok tube fitting does this. We'll show that in a little while on how exactly that works. Um, the way you deal with it in valves and other products is usually employ something else, a plastic, an elastic, a rubber component, elastomer, viscoelastic things, and they deform. Sometimes people use grease to form seals, and that's not a really great idea. And we'll talk about that in a minute too. So remember, continuous pore structures and surface finishes and is very, very important. The next thing to discuss is really permeation leaks. We're talking about this in a very simple form, again, not the metallurgy end, but just kind of explaining what's going on. When we deal with metals, what you'll see here on the left, as we look at this, we've got hydrogen running around up here as this dihydrogen or the hydrogen molecule, two hydrogen molecules together. Hydrogen will go through near the surface of metals. It will often go through a dissociation phase. What that means is this H2 breaks into two H's, hydrogen ions. Well, hydrogen ions are a term somebody's used before, very clingy. What they like to do is they like to take and look for electrons to finish their outer shield. Hydrogen hangs off a lot of different molecules. We talk about one of those big things that runs our world today being hydrocarbons. Hydrocarbons are carbon and hydrogen. That's it. Lots of carbons, lots of hydrogens hanging off the outside, and you'll notice that makes up very strong structures. Now, what hydrogen will do inside of metals is it will get up inside the metal and it will move in the little gray balls that are sitting there. We would talk about as being the metal structures, the metal grains of a grain structure of metal. Hydrogen can move between those structures. It's so small. And then it can go in there and start playing around and cause a variety of problems in lower quality product. So if the bonds um, between the molecules are not good, it can help break those apart and then go have something to now latch onto itself when it breaks apart a molecule and it's got an open electron field to be able to connect to. Um, that's a very basic way of saying this is how it starts to break things down. It can work at the end of cracks and hydrogen-assisted crack propagation and help those cracks open up as those molecules are breaking apart at the bottom of the crack. It can go in there and help it crack faster. So that's what we're understanding now today of the mechanism that's taking place. You can go in and find inclusions or different materials that were mixed into the metal and attack those or break apart weak bonds between areas and break it along what we call grain boundaries, the places where the different grains of the materials come together. So that's one area where it will go out and play. Now, there's something else, and happens in rubber. Now, in rubber, what ends up happening is you have the dihydrogen actually penetrates as dihydrogen. So it'll get inside the rubber or plastic materials. It'll diffuse through them fairly quickly. Um, and that permeation means that it can move all the way through the material and out the other side. So the trick and the problem with using polymers and elastic materials is that, again, you can have a very, very limited and low leak rate because it's constantly moving through that material. That structure is much different. You notice the grain structure and crystalline, organized structure of metals and a very disorganized structure of rubber materials. And what the hydrogen can do is follow in there. Now, when it comes to rubber materials, as we use them for O-rings and so forth, it's very important that they go through O-ring testing. Those materials need to be tested and qualified for use in hydrogen. Sometimes they shrink, sometimes they get bigger, sometimes they get bigger up to 70%, larger due to swell from the hydrogen because so much goes in there and hangs out. When you think about O-rings in a sealing area, usually that seal area doesn't have enough room for an O-ring to grow by 70%. So it falls in the category of bad things happen from an engineering standpoint. So when dealing with rubber materials, we actually go down to not just the name of the rubber, but the actual compound that is being compounded by a specific manufacturer. So doing things like saying Buna is not enough. Bunas are not often a good material. There are some that work and that work quite well, but as a general rule, it's not the greatest material. What we do find is that there are FKMs that work well at medium pressure areas. And then when you get into the higher pressures, we have found that peroxide cured EPDMs work very well. We've done a variety of testing on that. There are large studies being done on this. One of the big places is the Northwest Institute in Washington State by the Department of Energy is doing a lot of studies to really find better materials that are going to work within hydrogen in the future. Just understand, just saying a trade name is not enough. Now, next, we're going to talk about leakage and fittings and so forth. So what hydrogen does here is it'll work through where those seals are and go ahead and work their way out as dihydrogen. That is leakage versus permeation. So permeation moves through the material, leakage moves along the sealing areas and out. So we'll keep that in mind as we move forward on our journey here. Next is really talking about leak paths. This is a leak path formula and discussion of how to calculate leak paths. What I'd like to focus in on here, though, is really this L dimension, this length of the seal. This is a coned surface into a chamfer. Very, very short path here, very long path in the Swagelok fitting on both sides on the tubing and on the fitting. So we're going to concentrate on L. So what you need is a long path, a long area. What that does is reduces the ability for continuous pore structures, makes it an arduous path for that gas to get out. So being in product development for over 25 years at Swagelok, what I've learned is that the most difficult thing for us to do when we're dealing with fluid containment is dealing with gas seal performance. Gas seal performance is very, very difficult because of all of these issues. So one area that we can use to describe this is current technology that's out there. This fitting technology is called cone and thread. It's used very, very often on medium to high pressure systems. So pressures over 10,000 psi or 700 bar, clear up to 60,000 psi in these really high pressure applications. This fitting's been around for years and years and years. There's some misunderstandings about it in the marketplace, though. The first one is that uh, it is believed to be an industry standard that you can interchange products between manufacturers. That is not true. There is no industry standard for this fitting. It's kind of grown up from a project that started in 1918 by the Department of Energy in the United States, trying to develop high production of nitrogen after World War One. From that point forward, at that point, machine tools weren't that great. The only other type of connections they had were threaded. Thread forms weren't very good at the time either, so that wasn't a great option. How's this thing work? Okay, here's how it works. Take a piece of tubing, you put a cone on the end of it, you put a left-handed thread behind it, and you put this little collar onto that left-handed thread, and then you use the gland or nut to go ahead and push the collar that pushes the tubing into the cone surface, into the chamfer that's inside the body of the part. And the thought there is those two are going to slide together and create a long seal. The reality is that's not what happens. The reality is that the cones are typically at a sharper angle than what the body is. So what we see is you will have things like a body at 50 or a cone at 57 degrees, a body at 61. So if that's the case, if you have a sharp cone going into a shallow body, then the nose of that angle is going to hit and create a single line of contact to make your seal. So what you're going to do, it's good. You get a stress concentration at one point, which is one last piece that makes a good seal is stress concentration. However, it's only a single line. So you don't have that long L, you don't have that arduous path. The other problem is the cones themselves are often machined in a shop, in the field, um, and they really depend on the skill of the operator making them. They're not done on large rigid machines in a factory with high quality control with precision surface finishes. So chatter, which is vertical lines running the axis of the part along the sealing surface, lead to problems with continuous pore structures, groove marks due to bad tooling, not enough lubrication. And of course, the lubrication is they're sitting there with a little bottle squirting oil onto it. So there's no consistency in how that's done. So a lot of inconsistency on that primary sealing surfaces causes a significant number of problems. The way the collar is put on, how deep it is, can depend on whether you get enough drive in, whether you have enough threads of engagement. If you don't have enough threads of engagement, you don't have enough pressure containing ability of that collar and it can tear right off. The other problem is the gland to the collar interaction can lead to cocking of the tubing and actually causing the tubing to twist. So in order to keep those two from doing that, you have to put lubrication on the back of the collar. Well, you got lube running around. You might as well throw some on the nose too to make it so it seals better. And the problem is if you have grease making your primary seal, filling in those valleys in the continuous pore structure, that grease will eventually be pushed out. Gas loves to push grease and liquids out. Um, so what makes this really difficult is you go ahead, you go through factory acceptance testing, the system's sealed, it's leak tight. You go out and you do field approval and commissioning, system's tight. A month or two later, all of a sudden fittings are leaking all over the place. You're like, what happened? Well, what happened is the grease got pushed out, which was making the seal, and now you've got an issue. So you're going in trying to tighten up fittings, you're trying to remake fittings, and that can be a real problem. We hear that happening very often. Lastly, I like to say you'll see this weep hole or what's known as a leak hole. I like to say that cone and thread fittings have a leak hole because they leak, and it's pretty true. Um, they leak in oil, they leak in gas. In oil, you get a drop every now and then, not a big deal. In gas, you're going to have it continuously flow. Again, remember the size of the molecules being extremely small. A hydrogen molecule can be 100 times or 1,000 times smaller than certain other hydrocarbon molecules. So, having a very, very small leak in hydrogen means you're going to lose gas. Very, very small leak in hydrocarbon, the molecule is just too big to get through it, or not a lot of it's going to get through. So it's not seen as big of a problem. There's another issue that we've been seeing. This is some new learning about angled fittings. Now, this is not a cone and thread. It's a similar design. It's a 24-degree taper instead of a 30-degree taper. But What this is a coned fitting going into a body. The nut push is a little different. This is actually more consistent. Uh, see in the upper left-hand corner. These are von Mises stresses. Think about this like your radar. Red is a very high level stress concentration. Green and lighter colors get less and less stress that's being loaded into the system. So the first one under pretension load, what you'll see is that that fitting all the way around in this area where the body is and the fitting end is all red. They got a high level load concentration there that's making a good seal. But if we offset that tubing, so it's offset, it's pushed in this direction, pushed up by 0.3 millimeters, what happens is look along this body here. We went from being solid red to now greens, yellows, and if I were to zoom in, you see there's very few of those elements that are yellow along the actual sealing end. So under high pressure, that gas could leak right through here. Okay, so that's a problem. That's a leak. But this is the bigger problem that's happening. And we've been seeing this within the industry. Is people will say, my system was fine, everything was going along. My all of a sudden in a station, my hydrogen sensors went off, and I went back and we shut it all down and went and looked at it and we checked everything and there were no leaks. Well, what we found happening is that when you release the load on it, that side load, it comes back and it reseals itself. So what you'll see is that now we're not as red as we were up top, but we still have high levels of constant stress concentration along the sealing areas. This one resealed. If we push it in the opposite direction, so this time we're pushing it down, what you'll see is again, we're in yellows and greens all the way along the sealing surface. We were calling until we found this paper, we were calling this phenomenon burping. The systems would burp. I just recently spoke to a manufacturer for stations, and they said we think the sensors are too sensitive. That they keep going off, and I was like, hey man, you might have a different problem. We've seen other large manufacturers out there that have huge bunkering systems that thousands of fittings, and they randomly leak. It's random. Well, it's not really random, and in some cases, this could just be that your system design does not have enough play in it. Often within gas systems, we like to do things so that you don't have the ability of something like thermal expansion to pull sideways on the tubing. So good design would have things like pigtails or bends that allow the tubing to stretch some and act as springs so that it doesn't load the fitting, it loads the tubing itself. It loads that area that's designed to be springy. But these bunkering systems, what we saw was that parts of them were in the sun, parts weren't. They were really rigid between the two fittings, and you could see the fittings being pulled offset. So they're pushing against the wall of one side of the nut on the back, which tells us it's offset. So that's one of the things in cone and thread. We've always known it's been a problem in vibration, same type of thing, sideways loading. If you want to solve that problem, the ability to put on what we call anti-vibration glands that go significantly further in the back, like it might go all the way back to here, that can hold that thing from a side load and prevent a lot of that from happening, can be done. It's just additional expense and a lot of extra space to be able to do it. So anti-vibration glands can help that side loading condition. Something to pay attention to. Keep your eyes out. We might learn more about that as it comes along. So what do you consider in cone and thread? Well, there's no international standard for it. Different people use different standards. I've seen cones and bodies everywhere from 57 to 63 degrees. If you have two different manufacturers bringing them together, they're not necessarily going to interchange well. If you've already taken a part that goes in and makes a single line of contact and gouges into the material, or what we call coining to make that seal, you take one in that's a different angle, they're not going to meet in the same place. It may not seal at all. So moving back and forth between manufacturers, between designs, between tools may not work. You'll see this picture over here showing all the tools that go together to make a coning and threading kit. It's a lot of stuff that you got to do perfectly every time to make it work. Back to the skill of the operator and making that whole system work. So very susceptible to vibration failure and oftentimes require grease to create that initial seal. Again, that grease will be gone in a while, so it's not a real good seal. All right, so let's move into other fitting technologies. What else is out there? Real common, NPT threads. People love and hate NPT threads. Well, what we found another dissertation that was dealing specifically with NPT threads in hydrogen applications, and what they described was they said when pulling up and sufficiently torquing the NPT threads, what you'll find is that they will make a good seal as long as they have the proper sealing element on them. And they recommended 2 full turns of a high quality Teflon tape. Again, anaerobic seals, Loctite, even Swagelok SWAC materials, if they do harden properly, they can work fine, but oftentimes they don't if they're not put on properly. So then they stay in a liquid form and they can get pushed out. Um, so how does this work? Well, we call it wedging. So you've got a wedge down the axis of the part, so that it's an angle on an angle, and then you have a second one, which is every tooth itself has angle on angle, and by wedging all of those together, you eliminate the continuous pore structures. You put a lot of load onto those threads that end up helping to seal, and then you throw Teflon tape in between to fill in the gaps, and they can work quite well. I have done testing, certified the NPTs without much problem, and up through half inch. I don't know on the larger ones. So I think as you get larger, you have other issues, and that issue typically is getting enough load and enough torque onto the system to make it work right. So NPTs can work. They're not the greatest, but they can. The next one is one that pops up all the time, and this is BSPP with a gasket. So a British standard parallel pipe or an ISO G5 thread or 228 thread, which is a straight thread, a male body that comes into it that has a gasket on the shoulder that is metal with a rubber inner O-ring. Again, here's the problem. The O-ring material may or may not be compatible. These are fairly inexpensive on the open market. They you've got really no idea on their consistency. These are used very extensively for transducers within oil and gas industry. So people are trying to transfer that into hydrogen, maybe with success, maybe without. Again, problems here. If you get that axis of the part off to the axis of the body, so it's not perpendicular to the face, you have a very, very small crush zone on these. So you may or may not get the seal. Also, any waviness in that surface is going to give you problems. Very small crush zone, difficult to control. 3 manufacturers making the 3 different parts. So there can be issues here. The next one, people don't do this very often. I just don't recommend it. Don't put a tapered male into a parallel thread. It can, you're going to get lucky sometimes and it'll work, but it's not really a great idea. If you're going to do tapered, use tapered all the way along. Other types of technologies. Well, this is very similar to cone and thread, where you've got flares, and these are showing machined flares, but you could also flare tubing. Lots of different ways to make flares. Again, the problem is these two surfaces, if you'd want them to have as much contact as possible. It's kind of funny. I like the way this picture works because it shows red all the way along that. That's where the seal is. Well, not really. That's probably not where the seal is. It's not that entire distance. It's part of it or only a point, and single point of contact. Now, the one you'll definitely get single point of contact in all the time is on a ball on chamfer. So if you have a rounded nose and it goes into a chamfered cone, you're going to get a single line of contact. So that leaves you with, it better be really good in order to make it work. If you see this here, now remember back to grammar school when you took a ball and put it in a cone, you can see that's just one line that it would make inside. Same thing. So some people like these because they feel they can get misalignment on their parts better and line them up. But again, you only get that single line, and that's all you're going to get, and does not give you the long L, no matter what. Other types of technologies, O-ring face seal technologies. These can work at lower pressures moderately. We know a lot about O-ring face seals. We were the first ones to patent them back in the 60s here at Swagelok. These were used extensively on natural gas vehicles for all the connections. The problem with them is that seal under pressure cycling can move. So every time you pressure cycle and you depressurize the system and repressurize the system, it can actually move out. And when it repressurizes, it's a pressure assisted seal. So it's going to move. So you got to remake that seal every single time you run through a pressure cycle. That's a problem to start with. Second of all, it is a pure elastomer seal. It's not backed by metal to help with the sealing. So you're dealing with permeation rate all the time. Not recommended. Can tell you right now, German auto manufacturers have said not allowed on hydrogen vehicles. They used them extensively on natural gas, will not use them on hydrogen. So that's one just to avoid right out of the gate. Last is the SAE J1926, also the ISO 11926 fitting. This is using standard threads. There's another standard, I can't remember it off the top of my head, that uses metric threads. But the way this works, straight thread, just there to put load on. You tighten it down to the shoulder touching the body. That's where you run the preload. And in the corner, there's this funky little seal groove. It's not a chamfer. It's a little bit different. It's got a couple angles in it that an O-ring goes into. As long as they're put together well, they work really good. This is probably your go-to second seal behind what we'll talk about in a second in two ferrule fittings. But the way, but the problems are, here are the problems. People don't usually torque these and hit the torque specification. They take it to, that's tight enough. You know, the little grunt on the wrench when you pull it up, that seems good. And if you don't put enough load in, the pressure, especially in higher pressure hydrants, the pressure working on the face of that fitting will actually cause it to back out and overcome the stress of the preload. So that's a problem. The other place it becomes a problem is if you're going into aluminum components. The aluminum can be either under torqued and um, and that's a problem, or over torqued, which is more often a problem, where the aluminum actually stretches in the threads, and eventually when it relaxes, you lose the preload and it backs out. When they back out at 1,000 pressure cycles almost every time. They back out far enough that the O-ring comes squirting out up at the shoulder. When we first started going after trying to understand that problem, we thought we had an O-ring problem. It wasn't an O-ring problem. We gave O-ring enough room to get out. It's a gap problem, and it was an issue of losing preload. So those are a few of the items with SAEs. Ordering the right ones in the right pressure classes. You should not lube the threads on these. If you lube the threads and you torque it, you've changed your torque profiles, your friction profiles of the threads, and I have no idea what torque you need to go to be able to maintain that load on the surface. So stick with the threads as they are and go ahead and load it appropriately based off of the tables for your preloads and your torques. Other types of technologies. These are fitting technologies that use ferrules. So we're going to talk a bunch about ferrules here as we go. And we'll talk first about bite style fittings. So bite style fittings can come two ways. They can either be a two ferrule system or they can be a single ferrule system. What they rely on is a bowing of a piece of material. And then there's a sharp nose, and that nose drives into the tubing and bites. It causes a fairly significant stress riser that if you end up putting a load side to side on this tubing from behind, that stress riser can actually cause a crack and it could fail right there at that stress riser. So bite style is not good, especially in our vibration situations. Next one is, of course, the old, for our Americans, our Home Depot, Canadians, what is that, Canadian Tire? Your local hardware store makes stuff to go under your sink, usually in brass, usually not very good quality, and it'll be a single ferrule, and it relies 100% on friction, so it's just a friction fit. Not a great idea. Do not use nitrogen. Again, that's not enough. There's not enough energy there, enough design to be able to hold that entire load back, especially at high pressures. Another type of fitting that's out there in the market right now are manipulated end fittings. These are diesel fittings. There's two ISO standards that cover either the end of the tube or the body. The body is just a 60-degree chamfer, no big deal there. But the manipulated end is the curious part. So what they do is to go ahead and take a piece of tubing and smash it in a die to make it about the shape of what looks like a ferrule. So they can be rounded nose. Again, we talked about rounded nose and what the issues with those are. Ones that look like ferrules. This is an evolution of things like flare fittings. If you think about a flare fitting, often see them on brake lines on cars. You take a piece of tubing and you smash the end out to make it look like a cone. Use the idea of that part that's just been flared out and bring a fitting in. Well, it's kind of the same idea, just in reverse. You smash it to make it look like a fitting. What are the problems here? Well, when we started looking at these, we took one look at them and understood immediately. We do make a fitting that looks very, very similar to this, and it's called a port connector. So it's got a hard end on one side and then a tube adapter or something else on the other side to be able to allow you to connect close couple to fittings with a very, very short moment arm between the two. What we know about them is that they have a tendency to crack when you're in high cyclic loads. So things like at the end of a compressor where it's seeing a lot of vibration, what'll happen is they'll crack right here. They'll crack at the neck. So when we first started looking at these, we're like, ooh, this may not be a great idea. You've got a stress concentration load there. Maybe we should take a look at it. But if you say that, well, hey, these things work great on diesel, and we use them on diesel engines all the time at really high pressures. Why would this be different in hydrogen? Well, a very simple reason. If you look at this combination here, this is how a diesel fuel rail looks. A bunch of short tubes usually connected with runners between them that are either soldered or bolted together onto those tubes, multiple places, bolted to the engine, bolted to a fuel rail, bolted into the fuel injectors. When a vehicle moves, and we're under tons of vibration inside of a diesel engine, but this moves with it. So if the engine moves up and down, it moves up and down with it. If it moves side to side, it moves side to side with it. There's no secondary load coming down that tube. All right, so then there's this big long mess down here at the bottom, which is a fuel line for a light duty vehicle that could go from the back of the car to the front, 4.5 meters long, 40 bends in it. Um, this thing is going to see vibration a different way. It's going to see loading coming in. Now, oftentimes you talk about we do testing at X, Y, and Z dimensions and we don't see any problems. Well, that's not really the appropriate way to test a fitting. The appropriate way to test a fitting is to do what we talk here about. Instead of linear or planar torsional loads, we look at using rotational flexure loads and stress tests. And the way you do it is you take this, you take a fitting and you hold onto a piece of tubing. Now that tubing is held here, so it cannot go in and out, right? Or else it's going to blow right out and it's not going to work. So the only thing you have left is you have up and down and in and out of the screen. I can simulate that by rotating it in a circle. Now, so how do I go ahead and do this? Well, this test is actually pretty cool because what you do is you put a strain gauge on it, on the tube right here, and you measure the strain in the tubing because every tube might have slightly different strain, and you set your offset based on that. So your distance that you're going to make this rotation happen. So you do that, and the test is actually both an AS standard, an SAE AS standard, and an ASME standard to do the test protocol. It'll tell you what those stress concentrations you want them to be, and then you go ahead and run the test. Now, the other cool thing is that you go ahead and you pressurize this and can actually pressure cycle it while doing the test. That's a real test to see how things are going to fail. Now, if you have those bite style fittings, remember like way up in here where those bites are, what you'll find is that you put this type of load down the tube and they will snap right at the ferrules. And they'll snap at the ferrules every time. That's not a good idea. It's not a good thing. If the nuts aren't designed right and they're smacking the nuts every time they do this, then they'll snap at the nut. What we found when we did diesel fittings is we went ahead and ran these tests at the highest amplitude load. The ones we ran went about 800,000 cycles. The highest load they went about 3,000 cycles. The lowest amplitude load they went about 800,000. And the problem is this is supposed to be a 10 million cycle test. So my recommendation is this is the test we should be using to qualify fittings to go on to hydrogen, especially in hydrogen vehicles or hydrogen stations, where we're going to see loads that need to be done along those lines. So just be aware of that. That is a stress riser. The load characteristics within hydrogen are dramatically different. It's a place to pay attention to. All right, we're talking about material. We're talking about material characteristics as well. Let's talk about something a little bit different and what makes up good material inside a fitting technology or valve technology that you're looking at within hydrogen. The ASTM standard for 316 material, and this includes 316L. 316L material is primarily used with controlled sulfur, controlled carbon to be able to allow for better welding and more consistent welding. If you have sulfurs that are different in one part, you're welding to another part, can cause the weld puddle to shift. So you want to control those well. That's what 316L is used for. But the trick is that there's other characteristics. Nickel is always between 10% and 14%, according to ASTM, and chrome is between 16 and 18% of the material. Why is that important? Well, first of all, nickel is the single most expensive ingredient inside of stainless. So if you're making stainless at 316 and nobody's asking you for anything different, as a mill, you're going to make that at 10.01% nickel if you can. And the reason is you're getting more out for what you're putting in for sale. And in certain cases, that's fine. Not in hydrogen. The problem with hydrogen is hydrogen starts affecting materials up until you have 12% nickel in there to stabilize the crystalline structure. So anything below 12 really is susceptible to hydrogen coming in and affecting the way that material works. So what Swagelok has done is set our material standard at 12% nickel. You'll hear other numbers in the industry sometimes. Sometimes people are touting 13. It's really not necessary. We found that the benefits of going up to 13 are negligible. It's kind of when you get on that high end of the curve, moving from one number to another can be very costly to move from to get a very, very small increase in performance. And that's what we see. We also find that it's important to reach chrome level from 16 to 17%. That chrome and our moly all help with corrosion resistance. So corrosion pitting can cause cracking and hydrogen to be able to enter the material. So corrosion is something we want to watch out for. So combating hydrogen embrittlement, combating corrosion comes down to these two primary points inside your material characteristics, this nickel and chrome. You may hear another number out there in the world that talks about nickel equivalency. Nickel equivalency basically adds up a bunch of elements to get to a number, and that magic number is someplace between 25 and 29. There are people that are proponents for 28.5% nickel equivalency. Again, when we look at how the tests perform, when you take all the processes together, look how that deals with the performance under fatigue. There's a negligible difference between 27 and 28.5. All of our materials are at 27 to 27.5. Almost all of them, 90 some percent, are over 27.5. In those specific materials that are able to do that, they have 13% nickel. They add +1 on the nickel, gets them up to the 28.5. Again, we feel that economically, the gains you get are not worth going to that to start with. And second of all, we would rather control more tightly a few of the other elements and control our to be able to get a dual certified 316, 316L material. And that's Swagelok's approach. So we are in very good position with 12% and 17%. So you'll see that that's one very important piece about material characteristics. And that's across the board on all Swagelok materials that we can get them in 12%. So let's move from there. We've talked about a whole bunch of other stuff. Let's talk about tube fittings. So Swagelok tube fitting is known to be one of the best tube fittings in the world, and the reason is the two-ferrule design and the way in which it works. So there's three primary elements of the Swagelok tube fitting and its advantage, which is tube grip, gas seal, and vibration resistance. Let's go to the first one right now. We're talking hydrogen. Let's talk about gas seal. So what you'll see as you look at this product is you're going to see that the front ferrule, which is this ferrule here, the really long one, the front ferrule has two different major long sealing areas. There's a long sealing area along the tubing, a long sealing area across the body. The front ferrule has a differential angle. It's a steeper angle than the body. So when you go through the action of wedging apart or pulling it up, the rear ferrule is driven onto the front ferrule with an angle that lifts the front ferrule to a point that it raises up, slides along the body, and forms a burnishing action. Burnishing allows you to knock off the high points, fill in the low points with the material, plastically deform them, move them along without galling or welding them together. And that is the way in which we are able to get that very, very fine finish burnished along that area, reducing continuous pore structures and getting a long seal. So that's the front ferrule and how it works. Back ferrule does two different things. We get tube grip, and tube grip means pressure performance. And what happens is this ferrule, and it doesn't quite show it here, you'll see it on the next type of design, much, much better. But what it does is the nose of the rear ferrule actually dives into the tubing, gets under the surface, and cuts in, therefore being able to hold pressure from pushing that tubing back out. But more importantly, it stays, this whole thing acts like a spring, so it has some level of elasticity in it, allowing it to manage both vibration and pressure cycles as well as thermal changes. But most importantly, what it does is it also collets. So if you think about putting a drill into a large machine tool in a production facility, we use collets, and they hold on in a colleting action. It's not really a friction fit. It's a little bit different in the way the mechanics work. And we do the same thing within our tubes. So we hold it right behind that point where we've had the dive into the tubing so that we protect that nose area so it does not become a stress concentration point that would lead to a possible fatigue failure. So that's how we deal with that here. Now, there's a couple other things that come into play that we do. And one of those is what's called SAT12. It's our patented process. It's a low temperature carburization that we do on our rear ferrules. What we do, so the basic process is you take the ferrules. Now, stainless is stainless because it's got a clear coating. So you can't see any corrosion because it actually is always corroded to a degree with a clear crystalline structure oxide layer that's on the outside. We strip off that's and in vacuum furnaces and are able to see the base material. In that base material, we force carbon into the surface at a very low temperature, not to create carbides, and we create a very, very hard surface. What you see here in white. That hard surface is like tool steel, so it's able to cut into tubing and get that very good dive that we get for our tube grip. Finally, it has enhanced corrosion resistance, so it's actually even better in corrosion than an untreated ferrule. It gets great wear, but most importantly, one of the really, really important things here is that it does retain its ductility. So it does not crack when that ferrule is moving and diving and reshaping itself through its plastic deformation phase to get to the final grip onto the tube. So SAT 12 is a very, very important process. It is patented, and this is how we're going ahead and making those rear ferrules very good. We'll talk more about that in a second, in the secondary design. We do have the ability, and this is for primarily designed for OEMs for on vehicle, where they're used to using torque inside their factories. We do have an ability to make an assemble by torque two ferrule fitting, basically the exact same as what you see in your normal fitting. All the mechanisms work the same. The physics are all the same, except on the end of the tube, on the end of the nut, we have a crush zone that is in there that allows it to come in, touch the shoulder, and visually be able to tell whether it's tightened well enough because there's no gap, and as well be able to advance and crush more every time you remake it to get up to the standard 25 remakes. And this is assembled by torque with a torque wrench instead of by turns, which is the standard way. The reason we're able to do this is because Swagelok does have the ability to have gaugeable parts. In other words, we know all of the relationships of the ID to the OD of the part. We know when it's pulled up properly, allows it to know the nut has been advanced enough, and there's a gauge you can stick in or not stick in because it's a no-go gauge. If the gauge doesn't go, you know you've pulled up the nut enough. So that makes Swagelok tube fittings gaugeable. That we're able to use that zone to be able to make this crush feature work on the assemble by torque fittings. So let's move on to another fitting. So the tube fittings go up to the appropriate burst pressures for the tubing that they're holding. The fittings themselves are not actually rated for pressure. It's rated based off the tubing that they have. But that only gets you up to about 10,000 PSI on very thick walls on small sizes. Above that, you have to go to something different. And this is where the FK fitting technology comes from. This particular fitting was designed for hydrogen. And a few features you see about it right away. Well, first of all, it's a male nut. So it goes into a body, not around the outside of a body. It's sitting here on an arbor that's red. It has red ferrules on it, or somewhat red. Let's go back to that oxide thing we talked about a minute ago. We have this oxide layer that's clear. Well, we learned many years ago that we were able to manipulate that oxide, and if you grow it a little bit thicker, it starts working like a prism, and it changes the way the light bounces through it. So if you take a set of ferrules and you cook them in the oven for a certain period of time, they will start turning yellow, then brown, then red, as you raise the temperature and time, and then purple, then blue, and then actually goes back to clear after a while. And what it is just a changing of that oxide thickness. And right now it's thick enough so it's only letting the red, basically the red lights bounce out of it. So it gives it a reddish finish. Why did we do that? Well, we looked at it and said, hey, what happens if I'm building a vehicle or a system or a plant and I have high and low pressure? So I have two ferrules that are both, I have ferrule systems that are both high, medium pressure, FK style, and standard fitting. So I don't want them to put a standard front ferrule or a standard, worse yet, a standard rear ferrule into an FK fitting. So we changed color so you can't mix them up. Second of all, we have this arbor design, and we'll show you how that works in a minute in order to avoid some other failures. Basically, what it does is when you take this part, you take it out of the box, you take your tube, you cut it flat, you go ahead and you chamfer it, you take the burrs off, and what you can do is take this, screw it into your body till it's finger tight. The arbor will collapse, and you can pull it straight out. Stick your tubing right in, mark your starting point, pull it up one turn or pull it up by torque, and it's done. That's it. So you're able to put this in, ready to go. Everything's in alignment. You don't make any mistakes. And part of the reason for this is we found out that Unfortunately, in the marketplace, a lot of tube fitters, the first thing they do is take fittings apart to make sure their ferrules are there and make sure they're in the right orientation. Mostly because other manufacturers have not figured out how to make sure every single time they send their ferrules out in the right orientation and and make sure all the right parts are in them. Swagelok guarantees that within parts per billion accuracy, that they can come out of the box. You just slide your tubing in and go, and then pull them up. But when you take them apart, the potential failure mode of putting them in backwards, wrong, too many, is really high. So we want to avoid that. And especially in this medium pressure world, the arbor was the way we decided to figure out to do that. So again, this is a make up by torque or make up by turns fitting. It is gaugeable as well. It's make up to 1 turn, not a turn and a quarter like standard. That way it's not interchangeable. So we did lots of different things to make sure the basic mistakes couldn't be made on the field. It also uses eighth hard tubing, which is a little bit harder. It's like the cone and thread tubing is also eighth hard. They just get higher pressure ratings. So performance characteristics, how does this work? Same basics, except some different things that are in play. So front ferrule, lifted up, slides along the body, burnishes, uh, and gets great sealing service across the body of the fitting. But there's something a little bit different here. I don't know if you can notice it, depending on how big your screen is. Right there, the nose of the front ferrule actually dives as well. It's really cool because it does two things. The first thing it does is it um, allows us to get under the surface of the tubing and create our own surface. So if there's any surface imperfections, nicks, scratches, all those things, and if you think about it, a scratch is the perfect definition of a continuous pore structure. If you don't get it smashed out all the way, then it's going to just be a line that gas flows through all the way down. So uh, we have we get under the surface, we burnish, we make our own finish, and then we also get into some additional tube grip from that front ferrule as well for these higher pressures. Rear ferrule, you notice it looks a lot different. It doesn't have that big hinge in it. The reason is it's a lot more robust to allow us to hold much higher pressures. Um, so it still does do the dive that you see here, holding, biting into, or diving into the tubing to hold on, and it still does collet on the back action. So that's how the ferrules work, uh, giving us similar performance as a standard tube fitting, except at much higher pressures. Um, Again, we mentioned tube grip and so forth. Now, one of the things is that we do also SAT 12 this front ferrule, which is really important, so that we get that hardness on the front ferrule as well. On all of the sizes up through half inch, we do that. We do that. Plus, we also harden the nut to give us better actual wear resistance, just due to the amount of torques that we use. Larger sizes we handle a little bit differently. But that's how this whole fitting works. It takes all the knowledge of 60 years of developing fittings at Swagelok to develop a 4 hydrogen application. And I don't think I mentioned it earlier. We developed this in about 2004. We started in order to meet the hydrogen economy the United States was touting at the time. And it was designed specifically to go on vehicle for hydrogen. So hydrogen design product, designed for gas seal performance, designed for all of the other um, the other features that go together for hydrogen performance, and taking all that knowledge of two ferrule designs, overcoming all the problems with other fittings, flare style fittings, cone and thread fittings, O-ring face seals, and so forth, to get this effective tube grip and seal. Today, it is called an FK fitting because at the time we thought the market was going to be 15,000 psi storage pressure. So it was 15K, K for KSI. Of course, the market has moved to completely talking about bar. So now 1050 bar is the max storage pressures in stations, and 875 on vehicle. Um, the Also, this fitting has been re-rated up to 20,000 psi for 1300 and change bar. So FK doesn't really mean much anymore. But that's where it's at. And really, honestly, you can take a piece of tube, cut it off flat, shove it into the nuts and ferrules that have already been preset to its finger tight, pull it up 1 turn, and it's going to hold 4 times the 20,000 psi. So excellent design, designed exactly for hydrogen to meet all of your needs going forward. 2 ferrule fittings of the standard Swagelok, by far the best design for smaller pressures, FK for the higher pressures. And with that, we've pretty much wrapped up and kind of gone on a journey through what makes fittings work from continuous pore structures through long Ls, through dealing with permeation. And to solve all of those problems and all the problems with other fittings, you really build it together. And the Swagelok tube fitting and FK bring us that solution. And with that, I would like to say have a great day, and let's go make our world safe with hydrogen. Thank you.